Okay, hi everyone. It's now 5 minutes past 10, so with that in mind, I think we should get underway. We've still got a decent amount of material to get through today. We're definitely beginning to get onto the more advanced parts of the language now, which you'll probably see as just by the nature of what we'll be looking at. Um, the first thing we'll do was, if you remember, at the end of yesterday's last session on writing output to files, in file-based input and output, was I suggested taking a look at this exercise at the very end of that session. You might have had a chance to do that, you might not, but I thought it would be worthwhile if I at least were to go over the sample solution before we move on to name lists as the next topic. So what we were given was program 1.f90. So you're starting off from very little here. This program just creates a two-dimensional, a rank 2 logical array called map, which is mostly set false in this line, which just sets the entire contents of that array to false, and then it sets other parts of it to true. And you then call this write PBM subroutine, which comes from solution module, to write that to file as a PBM image. And you, of course, had to do all of this yourselves. If you were able to do that, you should have been able to make an image that looks like this. So hopefully you were able to do that. If you haven't, let's just take a look quickly at how you would do it. So this is the sample solution. You can check this yourselves. It's linked to here in these links, but you can see it's in the section 18 further functions. It is in the directories. I'll just pwd that if you want to take a look. Files, exercises, 18 further functions. This is actually a section that we'll be looking at in probably a couple of hours. So here's that same program again. It also actually goes a little bit further to write an integer version of that. I won't cover that, so we'll just look at writing out to file the logicals. So let's take a quick look at that, and that's pbm image.f90. So this is what you would be looking to write from scratch, essentially. You would be starting off module PBM image. That's the name of the module according to what we put in the program itself. Implicit none. And here we've made it private. So we've actually done a little bit more here. This has actually gone on a little bit ahead. But what we've done is we should have written a function here, sorry, a subroutine called write logical PBM. And what that's going to do is it's going to, here it's creating a new integer array. So this is called imap, and that's rank 2, and it's given the same size as, the same shape even, as map, the original logical array that was set up in the calling program. And rolling through this, there's a little bit that we'll do later on to take a look at this. So just looping through that, it's setting each entry of imap equal to map after it's been passed through this function logical to PBM. And logical to PBM is given just slightly above, I think, integer to, logical to PBM. And that just returns an integer value, which is 0, unless the logical value is true, in which case it returns 1. So it just converts false to 0 and true to 1. And then it calls this other subroutine write integer PBM. And this is where, remember we were spending some time looking at the format specifiers. And that's where this comes in helpful. And there's a little bit of magic going on here, I'll say, because we're using those internal file units here. So we're creating units. Oh no, wait, are we doing that here? No, actually, no. Sorry, I'm talking nonsense. We aren't. We're actually doing it the slightly easier way. So we open the file here. There's the file name that we've been given. That's just been passed through from the dummy arguments above. That's an intent in. The only thing that's intent out is the error. So this is doing some error handling as well. This is going all the way to try and deal with this file properly, I'll say. It opens the file, says it's formatted. We're going to write it status new. So it's going to create that file from nothing. And if a file with the same name already exists, this will actually return with an error. And it's going to pick out a good unit for us to use and store it in the variable, the integer variable my unit. Then it's going to start writing out some information. Remember that we saw from that Wikipedia link up here, we saw that the format has a couple of bits of header that we need to write in. So the first thing that we would put in is P1. So we write P1, and that's essentially saying it's a PBM image with a single bit of information, no more than that, just true or false, black or white. We can put in a comment if we want, and then we have to put in the size of the image. And this again, is not what we are maybe expecting, because images and matrices do not use the same indexing. We think of indices in terms of rows and columns, but actually for images we want to think about sort of x and y coordinates, I guess. So we actually put the number of columns and then the number of rows. And that's how we have to write it. So this is actually a little bit tricky. When you're doing this, when you're thinking about what is the size and shape of the image, and then how do I write that out into file, you have to really think about how to loop through that array. So we would be doing this actually in a way that doesn't feel entirely comfortable. Perhaps if you're thinking about arrays still as matrices, you have to flip it in your head. This is why I say it's sometimes a little bit unhelpful to think of arrays in terms of rows and columns. That can lock you into thinking about them in a way that then later on, when you come to do something like this, actually makes it a little bit more difficult. It's easier if you can to try and just think in terms of indices without attaching any hard physical dimension, I suppose, to them. So here we're looping through them. So we've got a loop. The external one is going to be over the first index, and the internal one is going to be over the second index. So again, this doesn't really match how this is laid out in memory. This works a bit better if you were working in C, for example. And then we just write the file integer to PBM IMAP IJ. So that's the array. We provide it with a format, which is a single character integer followed by a space, X. Remember, we saw how this worked in the formatting session yesterday afternoon. And this is doing all but one, because we're doing advanced no. So this is rolling through it, printing out each part, each element of this row. So it's going along all of the columns, one by one, and we've put in advanced no, so it doesn't do that carriage return to the next line that it would otherwise do. And then at the end of it, we do one final write where we do the same thing, and we don't bother saying advanced no, we don't have that here. And so that does do the carriage return. And then finally, there's that integer to PBM. Let's just take a look at what that's actually doing. That's here. And this just says that it's going to take in an integer and output an integer. So this is actually saying this is actually doing a sort of bit compression, I suppose. It's saying that if ival is 0, return 0. If ival is anything else at all, return 1. So this is sort of doing bit compression. This is a step you probably could get away without actually doing in your own code. So I wouldn't worry too much about that. The important thing, the important part of what this exercise is getting at is here, I suppose, because this is actually doing quite a lot. It's forcing us to think about how to loop through the array. It's forcing us to think about how to write out this array element by element, row by row. And then it's also thinking us, as part of that, you know, how do we advance through that? There is another way that you could do this, which would actually be to print out the entire row at a time. To do that, you'd have to write another format specifier, which would have the correct size. It would repeat probably this however many times. So if you have n cols, you would be doing you would have the value of n cols in here, and that would mean that you would have to write to a format string with that value in there. So that would be a little bit trickier. And again, this is where you can kind of see that Fortran doesn't exactly make this kind of thing easy for us. It's nowhere near as easy to use as Python, I think, in particular is. But this will work, so I'll just quickly run it. I don't think I actually am able to show you the image directly. Let's just quickly, let's just ftn PBM image and example 3. We will come back to this later on. Write PBM, really? Let me switch to module load plugin GNU. Maybe that's more helpful. Pull write PBM. Okay, I think the issue is in. I think this is waiting for us to do an exercise on it, so it's not quite correct. Right, I think we want to change that to write logical PBM. Let's just quickly do this. Vim example 3, and I think we want to change this to write logical PBM. Yes, yeah, that's right. Yeah, this is waiting for us to do something a little bit cool. But for now, I'll just change it to this integer PBM. So I'm bypassing what the exercise will be doing later is. Is it not write logical PBM? Oh, and I haven't made them. So I'm kind of ruining things for the exercise later on, but I'll change things back. Okay, so that now should have given us 2 PBM files. We can actually just open those. Let's just check logical PBM. Looks like this. Not very helpful. If I do less, a single line logical 49 PBM. And you can see that's the data that's in there. So I'm not going to bother to convert this into an image to show you. Although, I mean, I'm on Mac, I could probably download this. I could probably SSCP this to my own machine. And if I were to double click on it, it should open in preview. But you can hopefully see it's 0 everywhere, but we've got the ones down the left-hand side, the ones along the top, and the ones down the diagonal. and that's what we were looking for in the image. So hopefully that's giving you a little idea of how you might have approached this. If you haven't yet done this from scratch, I would try and bear in mind what I've just shown you. If you really need to take a look at the solution, and maybe just give it a go yourselves, see if you can pull it off, as it's a nice little way of bringing together a lot of what we've been talking about so far, putting it all in one place and asking you to really glue all those pieces of information together. But that aside, unless there are any questions, I'll just move on to nameless and we can get started with some new material for the day. I'll just see if anyone has any questions. Okay, I'm not seeing any. So yeah, I'll move on then for now to name lists. This I don't think should take too long. So I was considering just skipping this because it can be a little bit obscure. Typically people either need these or they don't. However, at least one person in the chat did say that they're using name lists at the moment. So I think it is worth at least going through quickly. So this is a special type of IO that Fortran does. It only really works in Fortran, though, but I imagine you can probably get libraries in other languages that will enable you to work with them, but they are there in the core of Fortran. And it's a way of grouping variables together for input and output fairly simply, actually. And this is actually a good way in particular of writing input files with options or configurations for runs, and in the same way dumping options and configurations internally from the program out to file. So it's a way that actually makes this pretty simple on the whole. It uses a slightly old-fashioned bit of syntax. You see syntax that looks like this quite a lot in Fortran 77, where you'd have some keyword and then the name of some structure inside forward slashes, and then a list of variables. So that's how we do this with name list. We say the name, we just say name list, give the name list a name, and then say what variables are going to go into it. A lot like this, where let's say we've got 3 integers, A, B, and C. Then we can create a name list called ints. That's just a name that we've chosen for it, and we'll say that in it we want to put A, B, and C. When they're in a file, so out of the program, just in a regular text file on your file system, it would look like this. It begins with an ampersand and then follows with the name of the name list, and then it's going to contain one by one on separate lines the different variables in the list and what values they have, and it terminates with a slash. The order of that doesn't matter, so you can have ABC, CAB, BAC, whatever. It really doesn't matter. Once it's in the file like this, so here's an example. So this sounds like a Taylor Green Vortex, which is a sort of CFD, a sort of standard setup used often for benchmarking fluid dynamics codes. So you could have a name list called run that contains some information about the simulation, for example, here. So it said, what is the name of the simulation that we're running? How many time steps do we want to integrate for? And how big do we want those time steps to be? You can imagine you could put a whole lot of helpful information in here. What you can do as well is you can put comments on there at the end of lines. So just the same as in Fortran, because Fortran will just almost treat it as internal. And then this is how you would then read it. You would start off by just saying, first of all, what are your unit for the I/O operations? So what is your file handle? And then you need to, of course, declare the bits of information that the variables which are going to go into your name list. You can see that we've used this way of declaring our string here, the name. We've just given it a colon, so we're allowing it to expand to however big it needs to be. Then we declare the name list itself, which we're calling run, that matches this. So you might notice this has to match back and forth between what's in the file and what's in the code. Open the file, just as we've always done. Here we're saying it's status old and its action is read. And we're assuming here it's just called config. And then all you have to do is read my unit run. So you give it here the name of the name list. Not a variable name, not a format or something. You just say read the name of the unit and then the name of that name list, and then you can close it. And at that point, you should be able to access and use name, end steps, and DT with the values that they were given in the file. Yes, anything that was set in the anything not set in the name list file will retain their initial value. So if there's anything not in here that is in the name list, it just won't get a value. So let's just quickly do this. Let's just quickly check namelist.read, namelist.read.f90. So I'll go down into that directory, which is 14. So let's just quickly look at it. Namelist read.f90 says that all we're going to do is we're going to open the file config.nml. We've actually given it a name here. Here we didn't give it a name. You don't have to give name list files any particular extension. Here we've given it the extension .nml. That's optional. It's really this is just to help us when we're looking in a directory. If we see a file .nml, it just tells us quickly that that's a name list file. It's just to help us, nothing else. But all we're doing is we're opening that file, reading it, and closing it. And let's just try to build that. So namelist read.f90, and we'll run it. And we can see it's printed out things from the file. What's in that file? Let's just open it, config.nml. We can see that's what we set in there. Let's just try changing that. Let's try changing config.nml. Let's change the name of the run to tgv my new run, which isn't a very good name, but it'll work. And if we just run it again, we can see now that that's using the name that we just set in the file. Okay. A couple of questions. What happens if the value set is not of the same type as the variable specification of the program? And what happens if we add something unexpected? So let's just try doing that. So the code, namelist read, was that it was going to read a character, an integer, and a real. So dt was a real. Let's try changing the number of steps to a float. So let's just change config.nml. Let's change this to 100.5 steps, which doesn't make sense. Ooh, that's interesting. Let's delete those. 100.5 time steps. Well, I suppose it does make a little bit of sense if you're thinking about time stepping. If we do that, it says that it can't match it, because now it's getting a float from file, but it's trying to match it to an integer, and so it's crashing out. So you have to make sure that the types do match between your name list file and the code that's reading the name list. The other thing to do, what happens if we add an unexpected value? What shall we add? Let's choose an integrator, which as we're just saying, let's use a Runge-Kutta Fehlberg 4.5 integrator. So let's save that. We're now providing some unexpected information. It cannot match it. So it's kind of giving a very similar error. Cannot match name list object to main integrator. It's actually saying the same thing here. It's saying 0.5. It's saying it specifically can't match 0.5 to anything. So it's sort of going wrong in the same way in both cases. It's getting information that it can't match to what's in the file, in the program itself. It couldn't match n steps to an integer. It couldn't match that integrator to anything at all. Okay, I think, yep, it cannot be matched to a variable. So reading multiple name lists. So you can have multiple name lists in the same file. So here we're adding some extra information about this imaginary simulation. Here we're saying what numerical schemes are we going to use. So you can do both of these separately, but what does matter if you do this, if you have multiple name lists in the same file, is that you need to be careful with the ordering that you use, because when you ask Fortran to read a particular name list from a file, it will scan through and keep on going until either it finds it or it hits the end of the file. If it finds the name list which you just asked it to read, it will read it and then stop there. If you then ask it to read a name list which came earlier on, that's now behind it. All it'll do when you ask it to read that second name list is, again, it will carry on until it finds it or it reaches the end of the file, starting from the place it was at before. If it's out of order, it will never reach it. It'll never find it. So in that case, you need to make sure that you probably rewind if you want to make sure that your read is independent of whatever order they're in the file. So we've now got this. So we've now got config full.nml. So let's take a look at cat config full.nml, and we've got three different strings to read: advection, diffusion, and transient. So let's try to quickly do name list read and have it read that. So let's create a new name list, and then I'll create the actual variables, which I've already forgotten. Advection, diffusion, and transient, weren't they? Advection, diffusion, and transient, I think. Advection, diffusion, transient, yes, and they're all strings. We'll create those the same way. We'll just add them on here: advection, diffusion, and transient. So we've got 3 more strings, but we're putting them in the schemes name list. And then let's just try and do this. Let's do read NML unit schemes with an S, like so. And then we can also just print them out. Print star advection, print star diffusion, we'll trim these to just get rid of the trailing blanks and print star transient. Okay, I think that should be it. Let's see if that works. So that's ftn namelist read.f90. That compiles. Does it run? No, it doesn't. Ah, because I've left in the integrator. Let's delete that. I know that's in the input, isn't it? It would also help if I had it to reading config full. Okay, let's try that again. Name this integrator. Did I leave in? Did I leave something strange in? Line 14. Config. I'm not sure why is it trying to read this still. Name list read. Ah, no, it did run. I'm completely missing that I actually did run it. I was stuck on the error up above. Okay, so that did actually run fine. So you can see it's got the extra information, and it stored those in the second name list. What we can also do, let's just try this. Let's swap the order. So I've now swapped schemes and run around. So it's now going to read schemes first and then run. If I recompile that and rerun it, we're now going to get an error because it's not been able to find read. What it's done, again, config full, is it's been asked to first of all read schemes. So it's come through line by line, and then it's found schemes, and then it's stopped at the end. Then we've asked it to read run, and it's already at the end. It's going to scan forwards, hit the end of file, and it hasn't been able to find run because run was actually way up at the top. So what we would need to do to make it work is to rewind an ML unit there to put it back at the start of the file, and then that should now hopefully work. And it does. Yep. And you don't do that, so that's what we've just seen. Okay, and how do we write a name list? It actually works very similarly, and it's again a very quick way of just dumping variables to file in a way that Fortran is going to be able to reuse. So if you again create your unit to handle the file, your integers, your name list, which will again say is ints A, B, and C. We put some values in them. Open the file. Now we've given it action write and status new, and then tell it to write my unit, comma ints. We don't have to worry about the format or anything. We just tell it to dump that name list to file and close, and that will give us this. Exactly how it looks inside here, it could format it slightly differently. So you'll see this is a little bit different from this. Here we didn't have commas before. I think this is what the Cray compiler has output, and the Cray compiler has used commas between items at the end of each line, and it's made everything uppercase. Remember, that doesn't matter. Fortran is case insensitive. It doesn't matter too much. So that's what it's formatted as its output. But you could then read this in the same way. You could read this using this code again, and that would work perfectly fine. Not that code. The code to read this. It would give you identical states in the code before and after. So writing them is just as easy, really, as reading them, and it's certainly a lot easier than reading and writing formatted data, because here we don't have to worry at all about the format specifiers. We just create a name list and let Fortran handle it to produce files that look like this. And these are then easily easily editable by hand as well. We can just open these in a text editor, as I just showed with the ones we were looking at here. Easily change them by hand, alter the parameters of a run or input data, whatever it is that you need it to do. So this is actually one thing Fortran, in terms of input and output, does make fairly simple. This is fairly handy for people doing simulations. So write a program. Here we've got a quick challenge. Do we have another one? Is it worth doing this? Write a program to write the simulation parameters as a name list so that it can be read by the previous example program. Do we want to do this? I think what we'll actually do, I think I'll just show this rather than actually write it just now, just to make things a little bit quicker. So if we take a look at name list write, and perhaps we'll do the next exercise. Is it not name list write? Or is it in? It's in the solutions directory, of course. Let's just quickly look in there. Name list write. I'd just like to catch up a little bit with some of the later material, so I'm going to try to speed through this if I can. So name list write would create the unit there, and then we've got this information. So we've got a deferred length string here, integer n steps, and real dt. We create those inside the name list, which we've just called run. Set that information, name tgv, and steps dt equals 0.1, and then there's nothing here I would think that would look confusing to anyone, I hope. We open it again, put the unit in MML unit, say that we're going to open that file. That's where we're going to write with status new and action write, and then we just do write NML unit run, and that puts these inside the name list in there, and then we close it. And that's all that there is to it. It's actually very, very, very simple. The only things that I think are new to all of you at the moment are this line, where we just create the name list itself, and then just how easy these read and write operations are, where you literally just say what is the unit and what is the name list. Okay, does anyone have any questions at this point? I think this is very simple, but if that's wrong of me and anything here is confusing, please do shout out just now. Okay, seems okay. Let's just do this last little exercise, and that'll be us finished here. So let's actually try this. We've got an example program, mainlist complex.f90. We're going to try building and running that, taking a look at the output to see how the structures are represented. And then we're going to modify the data and then just confirm that it's correct. I think we'll just do this very quickly. I'll do this along with you now if you're doing it yourselves. So let's just take a look first of all at Vim namelist complex.f90, see what it's doing. So we can see here what we've actually done is we've put a module at the top of the code. That's not normally what you would do, but you can do it. So that means that we can compile this entire application in a single line. It also includes a derived type, which we haven't done yet. We'll talk about those immediately afterwards. So don't worry too much about what this is about. We'll see in just a second what that means. But this is a derived type where we can create our own little packages of data, I guess, and work with those. And we're going to be writing that, and also an integer array called AOut, and that's going to be in the name list comp. We're going to fill these with information. We're going to say that the array is just going to be filled with the numbers 1 to 5, 1, 2, 3, 4, 5. And then the derived type, my type, which contains an integer and a real, is going to contain 42 and 3.14. And then we open it and write it. Let's just see what happens when we compile and run that. And what we should have is complex.nml. Let's take a look at complex.nml. And it looks definitely a little weird. It's a little strange. And comp, again, a equals 1, comma 2, comma 3, comma 4, comma 5, comma. You can see it's formatted a little oddly, but it is at least readable. It is still human readable. You could tidy this up as well if you wanted. And then also b percentage a equals 42, b percentage b equals 3.14 with a little bit of floating point error in there. So that's done what we would expect. It's created these, it's written into file. Now let's read. So we'll open again, and this time we'll I think we can reuse it. So let's do new unit equals NML unit. That should be fine. File equals complex.nml. Status should be old. And action should be read. And then we're just going to let's create a second. How shall we do this? How shall we do this? What's the best way? I think if we just let's literally just read it again. I think that's probably just the simplest thing to do. NML unit again and comp, and let's remember all that we have to do. Close NML unit. So now we'd be expecting that the variables a and b are now being filled with the values that we get back from the file, and we can probably just do something. It's a little bit quick and dirty, but it's not exactly nice code. It won't be formatted prettily, but we can just do print a, and then we can also do print star b. And let's see what happens there. It compiles, and it finds, cannot file exists. What's like? Ah, of course. So this is what happened. This is what's happening because here we've got status new. So the file exists, and we've said status new. So it's tried to open it as a new file, but it can't because complex.nml is already there. So it's raising an error. If we had put in errors here, if we had done error equals 99 or 900 or whatever, and then included some error handling, we could have got around that. It wouldn't have crashed out. It would have gone to whatever error handling we had put in. But because we haven't done any error handling at all, it's just given us the crash with a backtrace that isn't super helpful. Okay, let's try to run it again, and that time it's fine. And if we print out the information that we had in the file, it's all there. So this is now, we've set up the arrays internally and the derived type. We've written to file, and then we've read the values that we've just stored in file back in again and checked them. And that's what we've got. And if we check complex.nml, everything is there. Okay, I think that is everything. This is fairly short in comparison, this section. Does anyone have any questions before I move on to something maybe a little bit more interesting? Nope. Okay, that's great. In that case, let's move on. I do think, yeah, this is, let's move straight on to the next one is derived types, as I say. So let's move on to structures, derived types. So this is, I think, a little bit more computational. Again, we're sort of finished with input and output now. We're now going to head on to the slightly more advanced things. We will be brushing up against object-oriented type coding this morning. We'll see a little tiny bit of that here, a little tiny bit this afternoon, but not a huge amount. We don't cover that in the introductory class. So we've already actually seen a derived type, and we've seen lots of intrinsic types such as integer and character, but it is often very helpful for us to be able to take existing types and combine them together to make types of our own. So as I said a minute ago, sort of package data together, and that's what we call a derived type. And they're actually pretty easy to create in Fortran. It's quite simple. You say type : and then you give the type a name. And this one just contains an integer, which is called nmax, and an allocatable real rank 1 array called data. And then you put end type and the name of the type, which here is my type. And you then declare a new variable of this derived type by the same type, open bracket, the name of the type, close bracket, : name of the variable that you want to use. When you've got that created, when you've got your derived type variable sitting around waiting to be used, you can then access the components of it with what's called the component selector, the percentage sign. This is the exact same thing that we saw very, very early on Monday, when you're accessing the real and imaginary parts of a complex number, where we had z% RE and z% IM. It's the exact same thing. So if we've got our var of type my type sitting around, we can then change the nmax inside it by doing var %nmax equals 10. If we want to print out the data in it, we can just access it by var %data, and then doing whatever we would do with an array, just as we normally would. And you can also, again, you can create arrays of your types in just the same way. Here we're creating a rank 1 array of my types, which is now called var. And in that case, you would just make sure that you put your elements selectors of the variable after the first part, before the percentage sign. If you're using a derived type as a dummy argument in a procedure, in a function or a subroutine, again, there isn't anything at all different. You can provide intents. You just make sure that you declare it this way again in your in the specification part of your procedure. This again, just to briefly go back to sort of program design, again, this is where things like derived types are again the kind of thing that you would probably put in a module. You can put them anywhere at all. You can put them at the top of your program, but putting them in a module makes them easily reusable, because then whenever you want to use that type, you just use the module. Of course, the bad thing is being in a spot where you want to use the type everywhere, so you have to sort of copy and paste the type wherever you want to use it, and then you make a change to the type and you've got to remember to change it everywhere. that's the bad way of doing it. The much better way of doing it is to just put a type in a module, and then whenever you want to make a change to the type, you just change it in the module, and then everything which uses the module automatically uses the correct updated version of the type. There are a few features, and again, this is where we're sort of starting to head on to object-oriented type thinking, that do actually need it to be in a module. We're not going to talk about those, but it is worth being aware of that. So our strong recommendation here is that any derived types that you create, put them in modules. So how does it all work? And again, we'll see a little bit of object-oriented type stuff here. You have this as your formal type definition. You begin with the type. You can give that type some attributes optionally, and then its name. You can say that it's private if you want, and then you give it the components. So these are just things like your integers and real arrays that you actually want to store inside the type. That's what your component part is. And this is the object-oriented part, because you can turn types into objects if you then put a contains and start to list their procedures. This again isn't what we'll be talking about now. We won't be doing this today. This is for the intermediate course, but it can be worth being aware that if you want to write object-oriented Fortran, this is where you sort of start out. It's worth talking about data encapsulation here, I guess. So by default, when you create a type, everything, so the type itself and its components are going to be public. If you want to make that explicit, you put comma public in there. So that's one of these optional attributes. We can say that it's public. So that's just the same as default, but we're just being a bit clearer that this type and everything in it is public. You can also make what you call an opaque type, where the type itself is visible, is public, but everything inside it is private. So this is, this would let you create this. It would let you create variables of this type, but outside the module, outside the type itself, you wouldn't be able to access its components. If you did that, you just get a compiler error. Finally, if you're only intending for a type to be used within the module it's defined in, so this is if you're doing some pretty nice coding probably and making sure that everything relevant is sort of sticking together, then maybe you would have the type as a whole being private, and in that case you wouldn't be able to access it at all from outside the module. It would only be for use within it. So you can set up a derived type by doing things like this if you want. This is the easy way, I guess, of doing it, where you create your type and then you start setting the individual components within it to whichever values you want to use. var percentage nmax equals 10. Perhaps you would then allocate this array, and then you'd start setting the elements of data. But you can actually use something that looks like a constructor. Again, this does look an awful lot like object-oriented programming, because it's definitely headed in that direction. So you can use a constructor like this. So if we have a public type, again, we're just being completely clear here that everything in and of my type is visible everywhere to be used, and that contains an integer, a real, and a complex. And then somewhere else you would create a my type called A, and you can construct it in a single line by then saying that A equals my type. So you give the name of the type again. So you say create a my type called A, and then you say A is equal to a my type containing 3, which would be IA. 2.0 is going to be B, and then 1.0 is going to be Z. What you might notice there is that the order here does actually matter. So if we had put 2.0 before 3, we would have got a compiler error. If you have any allocatables, so any arrays, so if we had done the same here, if we tried to use a constructor to create my type, for the part of that constructor for data, we would have had to use null. We haven't really spoken at all about that. It's an intrinsic function that looks like this: null bracket bracket. So if we've had an allocatable array in 4th place here, we would have put comma null. That's kind of because we can't really declare, we can't say what's in an allocatable array until it's actually been allocated in memory. Until the point that it's been allocated, an allocatable array is just really an idea of an array. It's saying there will be an array, and we'll be using this name to refer to it, but at the moment it doesn't actually exist. So we have to use null when we do that in a constructor. You have to do the same for pointers. We haven't covered pointers yet, but we will very soon. And again, if you do have a pointer inside your type, you again have to use null if you include it in a constructor. You can also provide default values for your types, so you can just put equals whatever you want their default values to be. And then if you go through with that, you can very simply create any new variables with those defaults by just saying that they are equal to my type with empty parameters. And again, anything touching the memory, so allocatable arrays or pointers, would again come back with not allocated or null as their status from that. But yeah, as it says here as well, that isn't actually guaranteed. So some compilers can be a little bit iffy about this. So if you do this, you would want to probably put a null in there. So you'd actually put equals null up here for your array to make sure that the compiler is able to understand that. Why don't we? Do we want to do this? Do we want to do this? That could be helpful. Let's maybe quickly take a look at this. So we've got a quick exercise here, and then we'll maybe spend a bit more time looking at this challenge at the bottom. So here we've got a very simple random number generator in 2 files, module1.f90 and program1.f90. And that needs a few different state vectors, I guess. So, well, they come together, I suppose, to form a state vector, which are the multiplier, the c, the state, the increment c, and the modulus m. And you can choose what these numbers are. So this is a very, very simple random number generator. And there are good numbers to choose and bad numbers to choose. And what numbers you do choose will change the sequence of numbers that comes out of the generator. So we'll try to compile that first. And and then change some of the values of A and M to see what happens to the values that we get. And then let's just find out what happens when we make the components of the type private. So let's just take a look at that, at how this works. So let's go down to 15, is it? Oops. Let's go into, oh, it's 16. Why is it 16? Ah, yes, that's right. Okay, so it was module 1 and program 1. So let's try just taking a quick look at program 1.f90. Program 1 is just saying that we're going to use a module. We're going to create a type called myRNG in a variable called RNG, and we're doing the one-line constructor here as well by saying that it's equal to the default myRNG integer n, and then we're printing out the first 6 steps. And if we just take a quick look as well at module 1.f90, we can see that here's our module, and in the specification part we put our type myRNG. Here are the defaults. We've set some numbers for all of them. It's just for integers, nothing particularly complicated here. And this is just doing the work of the actual random number generator itself. It calculates a new value and returns it updates the state and returns the new value. So if I compile module 1.f90, program 1.f90, and then run it, you can see it's going through these steps. It's producing some numbers that you wouldn't ever use this as an actual production random number generator. It needs a little bit more work on top of it, I think, to make this useful. But you can see it's generating some numbers that don't particularly appear to be connected to one another, other than most of them being pretty big. So so let's now just see what we can do to change A and M. Let's just open the program. So this is us using the default myRNG, and remember that the default myRNG was this 4599110, and then a really big number. I'm sure that's probably a mass and prime or something, who knows. But now we can change what those default values are by just doing this. We just put in those same values in order. Here's some suggested bad values, 1, 1, 0, and I'll copy and paste this last one. Let's see what happens now if we run that. ftn and run, and we just get a very bad set of numbers, 1, 1, 1, 1, 1, 1. Definitely not random looking at all. But we can change this to whatever we want. Let's just change this to 3, for example. This is probably going to be horrible, who knows? It's still pretty bad. We can change this to 45, and this to 16. I'm just picking values, just like so. That's also pretty terrible. So you can hopefully see that's fairly simple how we just change the constructor. The important thing, I guess, is just to remember that these have to be in order, and that if you have anything allocatable or pointer, it has to be null. Last thing to check, what happens if we make the components of the type private? I think we can kind of guess what's going to happen. Let's edit the module. So vim module 1.f90. So let's make everything inside it private by just adding the word private here. Save and compile again, and we get some errors. And that's because now what we're doing is we are trying to access all of these components of my RNG, which are private. So actually, the compilers are being fairly helpful here. I was half wondering if the compiler would actually say these don't exist, but it's actually saying they do exist, but they're private, and you're not allowed to do that. We have a question. Why do you keep the public in the line above if we're making it private? Okay, so the reason for this is what we're doing now. So we've made this what we called in the material an opaque type, and that means now that we are allowed to create my RNG type variables, but what we can't do is access anything inside it. So in the code itself, in the program itself, what we are completely allowed to do is to create them. We can create RNG, we can create RNG2, we can create another RNG. We can create as many variables of type my RNG as we like. What we can't do is change anything inside it. So as it is, this code doesn't work because we can create my RNG, but we're never allowed to change anything inside it from the outside. So what would we need to do to make this work? What we would have to do then is we would probably have to do something like create a subroutine here, and we'd call it something like set my RNG. So you can probably see people here who know object-oriented programming and can probably see how this is really getting close to that now. We'd be doing a setter essentially for it. Set my RNG, which would take an RNG, and that would have a type my RNG. Oops, that's not right at all. Type my RNG intent, probably just out, I imagine, and we'd need to set here some A, S, C, C and M, and we'd call that RNG, and then we'd have integer intent in A, S, C, and M, and then it would just do RNG equals my RNG A, S, C, and M, and subroutine set my RNG. And I think now, if I go back to program and take this away, I should now be able to set this by doing call set my RNG, and I just give it RNG, and I'll just give it these bad values again. I think that should then work. Okay, it does work. Okay, that's great. So the whole point of this now is that by making the type public, we can create these anywhere. We can create these, but everything inside it is only workable from within module 1. So we're sort of working to kind of keep it safe. So this is what's called data and encapsulation. But what we're trying to do is we're trying to keep bits of our code safe from unintended changes happening elsewhere, if you like. We're sort of trying to keep them safe from one another. So by doing this, we're saying that my RNG can only be messed around with, can only be changed, can only be worked with from within the module itself. So that means that if we want to set the values inside it, we have to write a subroutine or a function, perhaps, if that makes more sense. Probably a subroutine, though, I would imagine here, within the module itself that does then have the ability to see and change the internal workings of the type. If we want to do my RNG equals ASCN from somewhere outside the module directly, we would be told no. The compiler gives this error above. Components, whatever, is a private component. It's saying you aren't allowed to work with that. Instead, you have to write a subroutine inside the module itself that does have access to these private components. Okay, does that answer the question there? Brilliant. Okay, great. Let's carry on then. So I think that's hopefully a nice little demo. We've seen all of that. So there are actually a lot of things you can do for derived types. What you can do is you can just use a format of star. So list directed free formats. You can just give it the type. And again, the printing that the write statement will do something vaguely sensible, maybe not incredibly sensible, but something hopefully okay. Or you can just print out the individual components, and you can write a format for each of those components. So if this is a real, you can just do a normal format for a real. What you can do as well, we aren't going to talk about it here, is you can actually write your own formats to be used specifically with the type to give, properly nice output. I'm talking about the kind of formats which would maybe take a type storing a date, which is a set of numbers, the 4/3/2026, today's date, and which would perhaps output to the screen, to your output handle, 3 March 2026. 4th March 2026 is the day, isn't it? However, we're not going to talk about that here, because that's very confusing, but it's worth being aware that that does exist. I personally don't think anyone ever actually really does that, but it is possible. Okay, I think it's worthwhile spending, let's literally spend 15 minutes doing this until past. Working on the diagonal structure again. So this array exercise we were working on yesterday, where we were solving this diagonal matrix, and we're going to change it to instead use a derived type. So we're going to create a derived type based on arrays holding those 3 diagonals, and we're going to change the code to use that matrix type. So there's a starting point here, exercise program.f90. So this is basically everything that we were trying to do yesterday. There's the program that drives it, and here's the module containing the workings. So this is maybe something, I think my solution was fairly close to this. Maybe you were also getting somewhere close with your own attempts, but this is probably what it would have looked like. This is actually doing a non-destructive solve. It's not deleting B in the right-hand side, which is what the original code did. But that's the code that we have there. And what we instead want to do is we want to have this derived type to hold everything in the matrix, and then a function that can create that matrix based on those diagonals, and then changing the solver routine to use the new matrix type. So let's see if we can spend time until 11:30 having a quick go at this. I'll let you all have a go, and then we'll maybe take a break and then come back and I'll talk about how you can do this. Okay, so let's have a go at that until 11:30. Okay, hi everyone. I hope you've been able to have either a proper go at that or at least to think about it. I'm going to suggest that just now we take a quick 15-minute break and we'll come back at 11:45 at 11:45, and then I'll go through how we would do this and you can watch me do it and see if that matches what you've attempted to do. So yeah, we'll be back in 15 minutes after a quick break. Hey, hi, welcome back everyone. I hope you've had a nice wee break there, a chance to stretch your legs and have a cup of tea. Let's get back then to, we were looking at the tridiagonal matrix program, solving the linear algebra problem. That's changing the sample code we had, the solution from the earlier exercise, to use derived types. So now the goal is to change the code which just uses arrays and so on at the moment to actually use a derived type to hold these different arrays together to make it look more like they sort of belong together. So what we need to work on are exercise program and exercise module.f90. I'll just quickly go through what I think looks okay. So exercise module.f90. Let's do this first, and then we'll work out how to actually use it in the program. So the very first thing that we want to do is to put here in the specification part of the module our new derived type. So let's create a new type, and that's going to be public by default, so we don't need to worry about that. Let's just call it a tridiagonal matrix. And then below, end type tridiagonal matrix. And inside here, we want to really have, at a minimum, those three arrays. I'd say it probably makes sense to also store, what was it? It was nmax, the size of the array as well in there. That way we don't have to calculate it again on the fly. So let's store nmax in here, just an integer, and then also those three arrays. So we want a real, and they're all going to be my kind. And there'll be dimension nmax is what they will be, except we don't actually know yet what nmax is, do we? We want to do we don't know how big the array actually is until the point that we create it. So that's actually going to be an allocatable, and that will be A, and then the exact same thing for B and C. So that and that, and we'll make that B, and we'll make that C. So that, I think, should be our type. What we now want to do is we want to be able to create that array. So what we can do is we can create a either a subroutine or a function. I think I'll do a subroutine, and I'll call it what will I call it? I'll call it create tridiagonal matrix. I'm feeling very imaginative today, as you can tell. And we want to do we want it to take those three arrays. Actually, let's do it BA. I was going to do ABC, but just below it's BAC. Let's keep that in order. That's upper, middle, upper, lower, isn't it? Diagonal. Oh no, A is the low. Middle, lower, upper. well, we'll stay consistent anyway. So we take the three arrays, B, A, and C, and we're going to return the matrix. And let's close off that subroutine and then fill in the middle. I can't spell that. Create tri-diagonal matrix. We don't need to put implicit none because we've inherited it from the module at the top. And all we need to do is we'll say we have three real my-kinds, and let's take a look at how they work here because they should be the same between the two real my-kinds and dimension 1 onwards. Intent in, because we're not going to make any changes to it, B, and then real my-kind dimension, and this will be 2 onwards for A. It will still be intent in, and then real my-kind dimension, and this will be 1 onwards again for C, because that's also starting at the top of the matrix. C, and then what's going back out will be a type of tri-diagonal matrix with intent out, and that's matrix. And all we would then really need to do would be to first of all work out what the size is going to be. So let's do matrix. We did size B before. Let's do the same thing here. So let's do matrix percentage n max. So we're accessing the n matrix component of matrix, and we're going to set n max equal to size of B. And then we can allocate, and we'll allocate matrix percentage B. And let's make sure that we're fairly explicit about where we're doing it from. So from 1 to matrix percentage n max, close bracket, and allocate. We could do this all on the same line. I'll do it on separate lines just to keep it clear. Matrix percentage A, and that starts from 2, remember? So 2, and that goes to matrix percentage n max as well. And then C is a little bit different again. Matrix has to percentage C has to start at 1 and carries on to matrix percentage n max minus 1. So remember, they represent different parts of the array. Again, these indices are a little bit confusing. Don't worry too much if you're just following along. If you haven't attempted, don't worry too much about the meaning of this here. If you are writing the code yourself, you should know what these bounds ought to be. That should make sense, I would hope. Okay, so we've done the allocations. In a real world, I'd be taking time to comment this properly so that we properly understood what it all meant. But now that we've allocated them, let's also just set B, and I'm just going to be explicit to make sure that it's completely clear that we're talking about arrays here. And we're going to allocate these array components of the matrix to the arguments that we've received in the subroutine. So matrix percentage C, again, everything should be just equal to itself. And that should be that, I think. So that should be us creating the matrix. Now, how would we do the subroutine that solves it? Something like this, probably. we would still take in the right-hand side and x. Those aren't parts of the matrix, but we would take in a matrix like so. We would probably just delete all these 3 lines and just put in that we'd be taking in a type tridiagonal matrix with intent in. Let's make it line up so it looks okay, and that's matrix. So we're now taking in a type of a matrix of type tridiagonal matrix and intent in dummy variable. We can still, does it make sense to still work with B? Yeah, I think it does. Let's say that we don't need nmax anymore because we've got nmax in the matrix. So let's allocate B local as matrix percentage B local equals B12 matrix percentage B local matrix nmax. Yes, matrix percentage, and R local should again be matrix percentage nmax. Matrix percentage nmax. So just the size of the matrix, that's what we're expecting. Size B, this doesn't work anymore, does it? We'll need to make these allocatable because we don't yet know how big we need them to be. So let's just make these allocatable. We don't know how big they are until we get them. We possibly could actually reference, actually, I'm not sure, I'm not entirely certain. Let's try this. I think this might actually be okay. Matrix percentage nmax. This could be okay. I'm not 100% certain. That might be okay. It might be able to grab nmax once we've got it there. I think it should do. So let's hope that that works. And here now, all we need to do should be to make these nmaxes, matrix percentage again, matrix percentage nmax, and then the A's and the C's we will need to add matrix percentage as well. So matrix percentage, just to make it clear that we're still using the ones from the derived type. I think that's possibly it. There's a C here. Let's make sure we do that. Matrix percentage, and under nmax here as well. Matrix percentage. Okay, that might be everything. I could have missed something, but at least that's everything that's sticking out to me. So all we need to do now is change the program to use the derived type. So let's v-split this with, what was it, program.f90? Exercise program.f90, exercise program.f90. Okay, let's change the program to use the new type. So what we want to do, we want to add in a new type tridiagonal matrix, and let's just call it mat for the sake of it. And let's call oops, have I just done things I shouldn't have done? Yes, type, I just undid that for some reason. Type tridiagonal matrix mat. Okay, that's what I wanted to do. I don't know why it didn't move me over before. Create tridiagonal matrix is what we want to do. So let's call create tri-diagonal matrix, and we pass to it the arrays B, A, C, and also the matrix that we want it to fill up. So then that should be mapped, ready to go. And then we should have to change tri-diagonal solve, which just takes the matrix as its first argument. So that hopefully is that. If anyone's also been doing this and spotted anything that I've missed while doing this live, please do shout out. But I think that is hopefully everything. Let's give it a go, and hopefully that will run. Exercise module and exercise program. It compiles. It's always scary when it compiles first time, I find. Okay, that's worked. Okay, so does that make sense to everyone? Was everyone able to follow along with what I was doing there? Any questions about that? Have the chat open. All good. Okay. We're taking things a little bit forward, so I wouldn't be surprised if there were any questions, but if you are following along, that's absolutely brilliant. Okay, great. So I would recommend everyone just take a quick look. The solutions are there, I think. Yes, so yeah, that's exactly what we've just, exactly what we've just done. And you should be able to open these and take a look. It'll look something similar to this in the solution code. And you should be able to have a go yourselves, compare it to what you've done, and hopefully, if anything was less than clear, you'd hopefully be able to clear things up. If, again, we are doing slightly more advanced material today, so please do get in touch. Send me a private message if you prefer, if you have any questions. Otherwise, let's move on to pointers, pointers and targets. This shouldn't take too long, I don't think. We're not going to cover this in a massive amount of depth. Pointers are certainly useful in Fortran. They have their place. They're not as useful as they are in, say, C. C, in particular, is very much geared around systems programming. Of course, you can use it for just about everything, but it really does have that kind of systems feel to it, I think. C is brilliant at letting you work with raw memory. It's brilliant for that. In Fortran, it doesn't really let you do that because it doesn't ever really expect that you would want to. However, for certain uses, pointers are still very useful. So they do exist in modern Fortran. I have a feeling it was Fortran 95 possibly, which introduced pointers. So they weren't even there in 90, I don't think. You create them and work with them fairly differently. If you are used to C and C++, pointers have a different feel, very definitely. You create them pretty similar, pretty easily. You just add the pointer attribute to any variable which you create. What you should always do, with pointers, is make sure that they are pointing at something. So remember, a pointer isn't a variable in its own right. It's a reference to another bit of memory somewhere else that is itself probably containing data, and you can have that point to either another variable, just some point in memory, or you can have it point to nothing at all. Very good practice is to make sure that when you initialize your pointers, you point them to something, and you point a pointer at something with this very special operator. It looks like a little arrow pointing at whatever you want it to point at. If you wanted it to point at a variable, you would just give the variable name on the right-hand side. But what you do if you want to have a pointer there but not pointing at anything in particular is what you shouldn't leave it uninitialized, undefined, because that leaves you unable to check it in certain ways. So if you want to have a pointer point at nothing, so to speak, you should point it at null, which we did speak about briefly in the previous section. So it's this intrinsic special value null, and whenever you have a pointer that's meant to not be pointing at anything in particular, you should always have it point at null. And the reason for that is that there's a difference between the pointer being undefined, which is to say without any specific value, without any specific state, and it being unassociated. Unassociated is saying, is it pointing at something in particular, or is it pointing at null? And it's important to be able to check that. We want to be able to say at some point, what is our pointer pointing at? Is it pointing at a variable? Is it pointing at a specific variable, or is it pointing at null? And you do that with the associated intrinsic function, like so. You say integer pointer p is pointing at null. That's how we've initialized it, and then we can do whatever. And then at some point in our code later on, we can say, well, if our pointer is pointing at a variable, then we'll do something. And so you say if associated p, do whatever. This will come back as false if it's still pointing at null. However, if we'd left it undefined, then it maybe wouldn't be pointing at null. It might be if the compiler's been helpful, but there isn't any guarantee at all that the pointer would be pointing at null. And if it weren't pointing at null, it could come back as associated p2, even if it weren't pointing at something meaningful. So it's up to us when we write code involving pointers to make sure that we always try to make sure it's pointing at either a meaningful variable or it's null. Otherwise, we can get some undefined behavior and our code may behave in very strange ways. So you can also have pointers to arrays. This does ask a question, how do we deal with arrays of pointers? We'll get to that in a little bit. So it's important to realize that when you're doing this, you are not creating an array of pointers. What you're doing is you're creating a pointer to an array. That might be a little bit strange, but remember, in Fortran, arrays are real things, they're real objects. So this is saying that the pointer is specifically pointing at an object of real dimension. Whatever. We don't have to specify the size of the array that it's going to point to. I should be clear about that. All we have to specify is the rank. So we're saying that P1 is going to point to any real rank 1 array. P2 is going to point to any real rank 2 array. Again, pointers are not quite the same as in C, so we can't just point at anything we like. If we want to make a variable available to be pointed at, we have to give it the target attribute. There's a thing here at anything of an appropriate type which is not itself a pointer. So pointers can point at pointers themselves or at targets. So you can point to another pointer, or you can point at a target variable. And it's the target variables like this. These are the real variables which we're actually going to be working with, which will actually hold data that we then expect pointers to be pointing towards. So we could do this, start our P pointing at null, have an integer called datum, which is going to hold some useful piece of information, and we're then going to allow pointers to point at it, and then later on we can do p points at datum. And at this point, the pointer is now said to be associated. And you can change it now using the pointer. So you can kind of think of this in a way at this point, if you aren't used to pointers, as this giving us the ability to use different names for variables. That's sort of a fairly simple way of using them. So if datum now contains the value 1, then we could assign a value to datum by having p point at it, and then assign the value 2 to it. So this is two different operations here. We're saying p is going to point at datum, and then whatever p is pointing towards, which is datum at the moment, is now going to be assigned the value of 2. You don't have to worry about things like dereferencing as you do in C. You just go ahead and do the regular assign operation. And you have a question in the chat. Would this still work if datum wasn't specified as a target? No, it wouldn't. If you tried to compile this without having the target on there, you would get an error. Again, this is because Fortran isn't working at quite as low a level as C. In C, you can just point at anything you like. There is nothing at all stopping you from just grabbing addresses in memory in whatever fashion you like and pointing at them. But Fortran is sort of hiding the memory from us a little bit. It's working at a slightly higher level, and so it doesn't like you to just talk about raw memory. It wants you to be able to work with internally what are objects, essentially. And another question, does a pointer and targets combination take up the space of 1 or 2 variables in memory? It takes up a little bit of memory, so you've still got the target. So this still holds as much memory, possibly slightly more. It'll take up as much memory as the base type, and I think slightly more to help with the target part of it. The pointer itself will probably be a lot less, because remember, a standard integer is going to be four bytes, plus probably a little bit of extra to help Fortran look after it, particularly if it's an array. The pointer is probably just going to be however many bytes it needs to reference the memory, which will probably not be as much. So it won't take up as much as two variables. It will take up a bit more than 1 variable. I think that should answer the question. Somewhere between the two, but probably closer to 1. It's sometimes a bit difficult, actually. Sometimes in Fortran, you have to actually measure the memory in very roundabout ways, particularly if you're working in MPI. If you're writing parallel code and you're in particular doing things like trying to move derived types across tasks, you can actually have to really jump through some hoops to actually work out how much memory it really does actually take up. It's not always entirely simple, but most of the time your objects will be, however many bytes and a little tiny bit more, and the pointers will just be however many bytes are needed to address that. Okay. Oh yes, associated can go a little bit further. So up above, we were using associated with the pointer to just ask, is the pointer p pointing at anything that isn't null, in which case it's true, or if it is pointing at null, it comes back as false. You can actually go a tiny little bit further, and you can also check if p is pointing at a specific target by just giving it this extra optional argument, target equals, in this case, datum, and that will come back as true if P is pointing at datum, otherwise false. So we have a quick exercise here. Let's do that together. We've got an example 1.f90. This is a broken version of the code from above. So we want to see what compiler message we get, if any, fix it, and then make sure that we can check its status with the associated function. So let's take a look at example 1. Is this 17? Yes. So let's just take a quick look at it before we do anything. Example 1, we're creating some variables and a pointer. We associate it, assign it, and print it. You've probably already seen the issue. Let's try to compile that. We get an issue. And this was what was in the question in the chat. What would happen if we didn't specify datum as a target? Error, pointer assignment target is neither target nor pointer. So this is saying what I've just been saying. If you want to have a pointer point at something, it has to be either a target or a pointer. So let's just quickly edit that again. The issue we've been told directly by the compiler is that datum isn't a target. So let's just add that. Make it a target. There we go. Datum equals 1. Integer is a target. And that should be it. Let's compile that. That now compiles. A.out datum is 2. So you can see what's happened. Datum equals 1, created a pointer, initialized it pointing at null, then pointed it to datum, and set whatever it was pointing at equals to 2, and then finally we printed datum. So we've indirectly modified datum here. The last thing to do was to just check if we can use associated. So let's just very quickly print star associated P. Let's just do this a couple of times here and here. Print star associated P. And I mean, for the sake of it, let's also have P point back at null again, just for the sake of it. So P is pointing at null again, and then let's print star one last time associated P, and compile that, and run it, and we get false to false, which matches what we would hope for. It was initially false because it was pointed at null. It was unassociated. Then we pointed it at P, and it became true. And then we pointed it back at null again, and it became false once more. I think that's everything we've just covered. Yeah. So I said above that one way of using a sort of simple way of using pointers is to sort of give things a different name. But we actually don't even need to use pointers if that's all that we really need to do. We can use what's called an associate construct to temporarily, at some point in our code, give a name to something. So this is helpful in particular if you've, for whatever reason, you've been asked to work with a very long, annoying name. This is a very simple use here. If we want to do that, we can, inside an associate block, inside an associate construct, we can give it a temporary name, and it does look a lot like a pointer. But you start with the word associate, and then in brackets say, we're now going to use the name P to refer to improbably or tediously long variable name, and then inside that block you can just work with P, and then when you're finished, end. When you do this, you don't need to have a target on your variable, and you don't need to declare p even. So this, in this case, this really is just giving a temporary name to some variable. You can do multiple associations at the same time. You just separate them inside the brackets in a list, a comma separated list. And that the select on the right-hand side of that can be either a variable or an expression as well. So let's just take a quick look at that. Now we've got example 2. So let's just compile and check that this works. Let's take a little look at it first. So we've got a real dimension 7 array R1, and this is also showing another use for it. This is showing we put 1, 2, 3, 4, 5, 6, 7 as floats inside that. But as we said, it can be as we said, the selector on the right-hand side can be a variable or an expression, and this is an expression. We're not just pointing p at R1. We're pointing it as a section of R1, and we're actually doing something a little bit complex by saying that it's actually going to refer to a strided section starting at 2 and carrying on in steps of 2. So if we do that, we'll say, okay, well, what's the size of P now? What is the data inside it? And then let's change it. And then at the end of it, we'll print out the original array R1. So let's try to compile example 2 and then /a.out. So the original array was actually size 7, but once we go into the associate block, P, the pointer that we said is pointing at R1 to stride 2, is a size 3. And if we print P out, we're only getting that section of it. And then when we change it and set those entries equal to 0, you can see 2, 4, and 6 have been set equal to 0 here, here, and here. So as well as just using associate to give names to easy names to things which are perhaps just taking time to write out every time, you can also use them if you're going to be, say, using the same section of arrays or using the same expression every single time. Another example could have been back in the tri-diagonal matrix code, which we wrote just half an hour ago, where I kept on having to talk about matrix percentage n max inside the subroutine to do the solve. I kept on saying matrix percentage n max, matrix percentage n max. If I'd wanted, I could have created an associate block and just said n max points to matrix percentage n max to just give it a slightly shorter, easier to use name. But here we can, completely change the way that we work with arrays through the use of associate blocks. Okay, let's quit that and go back to the material. Another thing to talk about, linked lists are a pretty sort of well-known, often used structure that pointers really make possible, I guess. In that case, you would have something like this. So you'd have a derived type, which represents a node on the list. And that contains, in this case, an integer datum, and then it contains a pointer to its own type. So this is type my node, and it actually contains a pointer to its own type of my node, which is called next. And then working with this, you would have to be able to add new elements to it. You'd also be able to have to write a subroutine to remove elements. Here, we're going to say that we're going to write a subroutine to add new nodes to this linked list. So we can, as we like, add a new bit of data to it. We can dynamically create a new node on that list. So we would just say, here's a subroutine, and its two dummy variables are head, which are a pointer, which points to the current head of the list, and the new data points to be added. And when you do this, you say, this is something a little bit new. You can allocate a pointer. So if you have type my node pointer p node, and then you allocate p node, it will create that in the heap and then point to it, and then have p node point to it. So this, what this is doing is this is creating a new p node, a new my node in the memory, and then setting p node to point to it. You can then immediately start working with it. P node datum is equal to the data that we've just received from the argument list, and p node next, we're going to say points back in the list, if you like. It's pointing to the old head. It's pointed to the next one in the chain, and then we set the current head to the same new dynamically created p node, and then the end. So in this way, we are creating new nodes whenever we call this, and then moving the chain along a bit. So this kind of moves on to a question. If we can create memory, if we can create variables dynamically in the array using pointers, should we be using allocatable arrays? If you're coming from C, it could potentially be more tempting to try and use pointers, just because that's what you're used to. But it's generally safer to use allocatable arrays wherever you can, which should in Fortran be most of the time, to be honest. The main reason is that when you use an allocatable array for a big chunk of memory, it will almost certainly be contiguous, which is what we want for performance. Pointers, it can be completely general, and depending on what happens, if you try to dynamically extend an array or something, what could happen is you end up with non-contiguous data, or it would have to stride somehow, even if you didn't do that. So there is potential for an array created through pointers in Fortran to not be as performant, and I think probably not as easy to use, to be honest, either. So really, most of the time you would want to allocate your arrays. On the occasions that's just not going to work, and you really do need to do something else, then you can use pointers. For temporary aliases, don't even bother with pointers. Just use the associate block instead to do that. There's one, I think, a couple more points to make. This is interesting. We'll try and finish soon, maybe, and then go for lunch, perhaps. Reallocating array storage. So pointers can help you do that, and you can imagine how that could be helpful. But we can actually ask Fortran to move and reallocate storage for us in a much more efficient way behind the scenes, without us having to get our own to do the extra work ourselves. Probably best to just talk through the example. So what we'll be using is move alloc. So this is an intrinsic function. Let's imagine that we've got a rank 1 array of integers here. It's allocatable. It's called I_orig. And let's imagine it's got some data in it that we want to keep. We want to keep whatever information is currently in there. But then for whatever reason, we need to increase its size. And again, if you wanted to, you could do things with pointers and to make this work. Probably the best thing to do in Fortran is what we're doing here. Let's say we've got n old, and we're getting some temporary rank 1 integer array, also allocatable, called itemp. What we want to do, our goal here is to have I_orig refer to the same data, but in an array which is now twice as big. Let's first of all work out how big I_orig is. That's with size I_orig, and store that in nold. What we can then do is we can allocate itemp at twice that size. We can then copy all of the data in I_orig into it, so that the same data from I_orig now fills up the first half of itemp. What we then do is we call this intrinsic move alloc itemp I_orig, and what that does is it behind the scenes, so probably working at the C level, if you like, it's going to move the pointers that are being used to reference to that array, but keep the name. So we don't have to worry about any of that. We don't have to worry about what pointers are being used or where they're pointing to. What we care about is that when we do this move alloc, itemp is forgotten about. It no longer points to anything, but the array that it used to be pointing to is now being pointed to by I_orig. So I_orig becomes the new name, if you like, for the memory that had been stored in itemp. So this means that we are able to double the size of the array that I_orig is referring to with a single copy. It's like renaming it. Yeah. Basically, yes. What this is doing, what call move alloc is doing, is it's saying there are two arrays in memory. One has the name itemp, one has the name I_orig. Now, let's wipe the name itemp off that first array and now refer to it as I_orig. So I_orig now refers to the memory that had been itemp. The old I_orig is forgotten about, and if you were to check whether itemp is now allocated, it would actually come back as the allocated. So we are having to think a little bit about memory here, but we don't actually have to do the work ourselves if we do this. All we have to do is create the new array, put the data into it, and then say, okay, swap the names that we use, swap the labels that we're using in the code to talk about these objects in storage. So this is the most efficient way to do this. There's a little bit of a challenge just to help you think about what's going on here. I'll actually give you a couple of minutes of real time to think about this, 1 or 2 minutes. Think about how would we do this if move alloc didn't exist? How would we double the size of I_orig? I'll just give you a minute, literally a minute, to think about that. If anyone has any ideas, hold them in, and then we'll ask people to type it in at the end of that. Okay, I don't think we need any more time than that. So of the people here, hopefully you've all been thinking about this. Anyone wants to type into the chat what they think? How many copies are needed to double the size of iReg if we didn't have move alloc? Anyone know? We would have to make 2 copies instead of 1, 2. Yep, you're both correct. Exactly. Let's take a look. If we didn't have move alloc, we'd have to do 2. So we'd have to do something like this instead. So we've still got iReg. We'd still have to work out how big it is. We'd still have to make a temporary array. First of all, we'd work out how big we want to be, just same as before. But then we would allocate itemp at the size of nold, copy the data from iOrig into it. So that's 1 copy. Then we would deallocate iOrig. Then we'd have to allocate it again at twice the size, and then copy the data from temporary storage back into it, and then deallocate itemp. So that's two copies, this and this. So that's twice as much work. It's certainly slower, particularly if it's big. If it's big, you could potentially see time being used just to do that. And actually, there is even actually a little bit of a overhead in doing the allocations even. And again, if the arrays were big, you may not even have enough space in memory to hold both arrays at the same time like this. So move alloc does make things more efficient. We only have to do that 1 single copy and then swap the names around, rather than copy to temporary, deallocate, reallocate, and then copy back into storage. It just saves us a little bit of time. It saves a few lines of code as well, as you can see. So it's something that can help. You wouldn't always want to bother with it, but it can definitely be a boost. This is the final section, and then we'll stop for lunch, I think. So I mentioned up above that, where was it? That these here are not arrays of pointers, they are pointers to arrays, because as I keep on saying, arrays are special in Fortran, they're their own structure. So a pointer to an array is different from a pointer to a scalar. They're different types of things. So how then would we create a pointer to a rank 1 array? So how then would we create a rank 1 array of pointers? We can't just add dimension to it, because all we're doing then is creating a pointer to arrays. We need to do something else. This is tiny little bit clunky. It needs us to do a little bit of work ourselves. We need to wrap it in a type, essentially. So what you can do, you create your own derived type. You can call it whatever makes sense. Pointer real rank 1 is what we've called it here. And inside, it just contains real dimension colon pointer p. And that's initialized by default as pointing to null. Then once you've wrapped it in that type, you can then say, give me an array of that type. So you can see we've by doing this, we've kind of obscured the pointer within the type. So that's when we then say dimension 10, we're talking about having an array of the type. What is that type? It just contains arrays. It just contains a pointer to this type of array. And at that point, we can then say A1. We can talk about whichever element of A that we like, and access the pointer within it. And that points to, well, in this case, null, but we could point it to any real rank 1 array that we wanted. Okay, I hope that makes sense to everyone. I think we'll finish this section here, Does anyone have any questions just now about any of this? Pointers could be new for some people. Um, for other people, they could be super old, super used to them, very, very used to using pointers. So does anyone have any questions? This could be very easy or very tricky, depending on what your background is. Okay, everyone seems happy with this. In which case, I think we'll just leave things there in that case for now. We've got one final section of actual material. You might be pleased to hear this. We'll break now for lunch. When we come back, we'll do this new section on interfaces, which we've mentioned a couple of times. We've mentioned the contract block and how using a module means that a lot of the time you don't have to use interfaces, but there are some cases where interfaces are helpful, so it's worth knowing about them. It opens up a lot of neat things for you, and particularly if you're heading down the polymorphism and object-oriented type routes. So we'll come back to this after lunch, and this is the last real section of new material that we'll be covering. Then we've just got a couple of light, helpful things to know sections, and then we'll just really be working on exercises as long as people here want to. But we'll break for lunch. We'll come back at, let's take 50 minutes and come back at 1:30. So yeah, hope you have something nice to eat, a little break, answer your emails, and I will see you back here in 50 minutes.